So now I'm going to show you what to do with all this using number 16. So number 16, what I've done is I've drawn the figure here that it's talking about. This is the R figure, and we want to convert this to an S figure. But let's just see how you start this problem. You may want to pause the video and read it. We have a double integral over R of 4x plus 8y dA. And so we're going to convert this to a double integral over S. And they're already giving us the formulas here for X and Y right there. So you plug those in to get the double integral in terms of U and V. So wherever there's an X, I'm going to put a 1/4 times U plus V. And then wherever there's a Y, I'm going to put a 1/4 times V minus 3U. Now what they did was they did a lot of the work for us already, and so we didn't have to do that. But then what I need here is I'm going to put du dv or du dv du, but I need my Jacobian. I need my Jacobian right here. That's what we're going to figure out in a second. So before we do all that, let's just figure out what this integral is. Just the basics of it, the interior, excuse me. So this is equal to double integral over S. We're going to figure that out in a second. Of U plus V plus 2 times V minus 3U. We're going to take care of our Jacobian in just a second. And now, I'm sorry, that should have been dV. du dv. And let's go ahead and simplify this. This is double integral over S of, what's this, U plus V plus 2V minus 6U. So that would be 3V minus 5U. Then we have our Jacobian that we're going to figure out, and then times du dv or dv du. All right, so now the limits of integration for S, we need to figure those out. So what you do is you come over here and you take what, I'm going to erase this for right now. You take what they gave us and you find an expression for its boundary. So if it were a circle, you'd find the expression for the circle, or an ellipse, whatever. And so what I did was I labeled the points that they were given to us, and then I found the equation of each line. So if you look at AB and CD, AB and CD are parallel to each other. So what I'm going to do is I'm going to take those two and I'm going to put those together. I'm going to move the x's over. Y plus 3x equals 0, and then y plus 3x equals 8. And then the other two I'm going to put together as y minus x equals -4, and then y minus x equals 4. Okay, there's more than one way to do this, so if you see a different way, you can do it. So I'm going to let u equal to y plus 3x, because that's common on both sides, and u goes between 0 and 8. And then v is going to be the y minus x, and v goes between 4 and -4. So this is another box. And so what S is going to be, it's going to be U is V. V goes between -4 and 4. So that right there is 8. And so this here is S. So we have a transformation going each way. One is the inverse of the other. And so we're going to integrate over that. So now this integral becomes double integral. I guess we'll do u last, 0 to 8. 0 to 8. V goes from -4 to 4, 3v minus 5u. And now we figure out our Jacobian. To figure out the Jacobian, you have to get the x in terms of u's and v's. So we'll do it up here. My Jacobian will be, it will be x sub u, which would be 1/4, x sub v, which would be 1/4, y sub u is -3/4, y sub v is 1/4. Determinant of this, 1/16 plus 4/16, no, 3/16. And now this is 4/16, which is 1/4. It's already positive, so that's okay. Leave it positive. This becomes 1/4 here, and then I think we were going to do dv du. That's a pretty simple integral to solve. The answer is 192 when you do the math. All right, so that's essentially what we're doing here. We're just taking something that's complicated to integrate over. Notice the integration over this would be difficult because, well, it wouldn't be too bad. I think it would just be two different integrals, this one plus this one. But your boundaries are lines, and here with S, your boundaries are horizontal and vertical lines, which are easier to work with. This one right here is good. Let's try number 18 next. So in number 18, what we have is a sideways ellipse. Looks something like this. The reason why I know it's a sideways ellipse is because it has the x squared plus the y squared, and then in here there's an xy term. If ever that's the case, it's a sideways ellipse, which means that its major and minor axes are not parallel to the x and y plane. So x and y axes. But they do give us the conversion here, and if you plug these in to this here, we can try this. Let me do it in black so it's better to see. So everywhere there's an x, I'm going to put a square root of 2u minus the square root of 2/3 v. So I square that, minus, and then x times y. Let me write all this out and I'll come back. All right, so here you have it. So when you square this out, you get 2u minus 4/3 minus 4/3 plus 2/3 v squared. This is a u squared minus a 2u squared. The interiors of these cancel, and so that would be plus 2/3 v squared plus 2u squared plus 4/3 uv plus 2/3 v squared equals 4. When you combine like terms, the 2u squareds here canceled, the 2/3 v squareds, so 2, so we get u squared plus v squared equals 1. So what they've done for us is they've done the heavy lifting of converting this ellipse into a circle of radius 1. So this is a uv plane. That's u squared plus v squared inside of there. And then this ellipse is x squared minus xy plus y squared equals 2. And in the scheme of all this, the top one, this is the r, and the bottom one, this is the s. So we're going to take the integral over r and convert that to an integral over s. So there are a couple things we need to do. We need to go ahead and plug in what's inside of here. Well, we did that here on the left. So what's inside of there is double integral of u squared plus v squared. It just so happens that what we're integrating over, what we're integrating, the integrand is the same thing as what we're integrating over on the left. That's not always the case. This could have been inside here just x plus y or something. I think it's just to make this problem easier that what we're integrating over, which is this ellipse, the left side of it is the same thing as the integrand here, okay? So then we have the u squared plus v squared on the interior. There's going to be a Jacobian here. And then we're going to do some sort of dv here, or dv du, dv there, okay? Of course, this will be over s. So s in this case is x squared plus y, no, I'm sorry, u squared plus v squared is 1. So now we find the Jacobian. So let's dig over here and take the Jacobian of this thing. So it's x sub u, which would be square root of 2, x sub v, square root of 2/3 negative, y sub u, square root of 2, y sub v, square root of 2/3 negative, positive. So this would be 2 over 3 plus 2 over 3, which would be 4 over 3. Yeah, so multiply by 4/3. So this Jacobian now becomes 4/3. Oops, I think this is square root of 2/3, like this. So that would be square root of 3, square root of 3. And now this is 4 over square root of 3. That goes 4 over square root of 3. And then this u squared plus v squared, it actually multiplied to 2 times that. So I'll multiply by 2. And then what's funny here is that now we're going to do another transformation. We're going to change this to r and theta, 0 to 1, 0 to 2 pi, and then 0 to 1. U squared plus v squared, we're going to call that r squared. We're going to multiply by the 4 over root 3, and then this du dv, that becomes r d theta. So let's do the math here real quick. This is 8 over root 3, double integral, 0 to 2 pi, 0, 1. And then that'll be r to the third dr d theta. When you, so now we do 8 over root 3, integral 0 to 2 pi, it's 1/4 r to the 4th from 0 to 1 d theta. This all becomes 1/4, so this becomes 8 over root 3 times 1/4, this is 1/4. And then integral 0 to 2 pi d theta, this just becomes theta out of this. So this is 8 over root 3 times 1 over 4. Theta from 0 to pi is 0 to 2 pi is 2 pi. So this is over 2. I think this is 4 over root 3 times pi. And that's the right answer. There we go. So what do we do? Well, we converted something that would have been really difficult to integrate over, this sideways ellipse. We converted it to a circle using their conversions that they gave us, not easy to find. When we did that, there is a change in area. So we found the change in area, 4 over root 3, and we multiplied through by that. We multiplied it by that. This is my Jacobian right here. And there you go. That's that problem.